Hi guys. In this second video I will cover some of the NMR concepts in the NMR handout. These 5 concepts are listed here at the top of this page. The first concept we'll look at is number of signals. Number of signals that we expect for a given compound. First off, we see some examples here. A variety of compounds. Let's just go through these and see how many signals we expect. Ultimately, you should remember that we get different signals for different proton types because different proton types are going to have different delta E's. The different delta E's come from different proton types having different electron densities nearby. Ultimately, we need to be able to identify when types of H's are the same or when they're different. Now this should be pretty straightforward because when they're different, they're different. There'll be some cases where we think they're the same, but it turns out they're different then as well. Ultimately, let's just do some examples and see how we do. This first compound here, we have 3 proton types, the CH3, A. Now all 3 H's are the same. Okay, there's free rotation, and all 3 H's there are NMR equivalent. We're going to call those A. Then we have the CH2. We'll call those B. But then we have this other CH2. These 2 CH2 groups are different because one is closer to the bromine and one is further away. If we draw this line bond, I don't know if that helps any. CH3, 3 different signals here for proton. Again, we're doing proton NMR. All right. Everything we do here early on is proton NMR. And you will know when we're doing carbon NMR. 3 signals. By the way, which signal should be most downfield? All right. This is exact peak position, but we can talk about that. Most downfield should be this signal for C. Why? Because the bromine is electron withdrawing, and it's going to serve to de-shield signal C, or these H's. And the de-shielding tails off as we move further away from the electron withdrawing bromine. So that bromine sort of takes away some of the sunscreen from the CH's. Doesn't allow those electrons to sit here as much to shield. So the bromine serves to de-shield. Okay, that's just a little bit of review and also sort of foreshadowing. Let's concentrate on number of signals. This compound, 2 signals, so that's 3. You can barely see that there. That's 3 signals. 2 signals here. We have symmetry. The 2 CH3s are identical. We can draw this compound like this. Okay, but that's A and A. We're looking at CH3s. And then this H here, that would be B. All right, 2 signals. This compound, well, the answer is already given for most of these here. It's A, B, and C, 3 signals. Let's just confirm why. Are the 2 CH3s the same? No, one's bonded to oxygen, the other's not. They're going to have different electron densities. The oxygen is going to pull more on this CH3 than it can on the other one. And then the CH2 is unique, 3 signals. On the other hand, this ether, dimethyl ether, 1 signal. All right? The 2 CH3s are identical because of symmetry. This ether here, what is this? Methyl tert-butyl ether. Methyl tert-butyl ether. Problem is that's sort of backwards. The tert-butyl should come first. Tert-butyl methyl ether. Anyhow, how many signals here? Well, the answer is 2. We have these 3 methyl groups are all the same. That's 1 signal. And then the CH3 bonded to the oxygen would be a second signal. All right. The third topic will be integration. We can go ahead and sort of foreshadow that a little bit. The integration is going to be 9-3 for the 2 signals. Or we can take that down to 3-1. The integration just comes from the number of H's that are for each signal. All right, but one of the powerful things about NMR, though, proton NMR, is that the signal height, the signal intensity correlates with number of hydrogens, and we can use the signal height or the integration to tell us how many H's each signal is for. Okay, let's stick with number of signals. 2 signals, yeah. The CH3 and then the CH. Alkenes here. Obviously 2 signals, A and B. These 2 methyls are equivalent. And these 2 hydrogens are equivalent. 2 signals. But how about this alkene? Here we have 3 signals. Here, these 2 H's are not the same. One is trans to the bromine and one is cis, and we don't have free rotation here. See, back over here, the 2 H's were the same because they were both cis to a methyl. And they're both trans to a methyl. Okay? They're identical. But here, these 2 are not. And of course, the C hydrogen is different because it's on the carbon that's bonded to the bromine. That's certainly different from the other hydrogens. 3 signals. Okay, a couple of aromatic compounds. This is benzene here, 1 signal. All 6 protons are the same. Hopefully that's pretty sort of straightforward there. But if we look at this compound in which we have a benzene ring with 1 substituent, with the remaining carbons being substituted with just hydrogen, or there's no substituent, we expect 3 signals. These 2 are the same. These 2 are the same. And then that one. These 2 are in the same relative position to the nitro group. And then these 2 are in the same position. And then that's the third. We'll do some other examples of aromatics below. Okay. There are ones down here for you to work on your own. And I think the plan should be that we'll do these in class. Okay? We'll look at these in class. Basically, how many signals do you expect for each? Proton. Okay? We're doing 1H. All right? Now eventually we'll look at carbon NMR and we'll focus then on the carbons, but for now let's focus on the hydrogens. Here's a couple of named compounds that we may or may not see during the course. Okay. There you go. Give those a try on your own. Let's look at this one over here on the left, though. It's already assigned. We did some alkenes where there's a lack of rotation because of the pi bond. Let's look at this ring here. It's a cyclobutane ring. How many signals? A, B, C, D, E. Looks like 5 signals. Well, that just comes from counting the A, B, C, D, and E. Okay. Well, HE is clearly unique because it's on a carbon bonded to the chlorine, and there's no other H in that situation. What about these two? They're both on the same carbon, but they're not the same. Because HD is cis to the chlorine, where HC is trans. They're not the same. All right. Now, electronic effects, okay, which ultimately, okay, this B local is due to the electrons. This is an electronic effect. The electronic effect occurs through bonds, but it can also occur through space. Because the electrons being closer to each other can sort of perturb each other. So ultimately, HD is closer to the chlorine and HC is further away. That's going to lead to a difference in NMR. Over here the same thing, but these two H's are the same. Those are both HC, these are both HD. And then these two are different because they're on a different carbon, and it's not the same as that. Because this carbon's bonded to the carbon with the chlorine, but that carbon's not. And HA is trans to the chlorine, where HB is cis to the chlorine. So 5 signals. Okay, but give these a try here on your own, and we'll look at those in class. Okay, the next thing we're going to look at is peak position. Where do we expect these signals to occur in the NMR? But I see before we move on to that, give you the NMR of phenacetine here. Number of signals, all right? Now you can't cheat because the number of signals are shown over here, all right? Don't look. Determine number of signals, number of 1H signals, but also number of 13 carbon signals, or just carbons. All right, we'll talk about how many unique types of carbon are in this compound. Do that as well for phenacetine. Okay, if you have any questions, you can ask, but we will cover that, so think about that ahead of time. Otherwise, we will not be covering carbon until later in the handout. Okay, but then I give you the H NMR and the carbon NMR of phenacetine on the next page. But don't look at it. Don't cheat. Okay, well, let's move on to peak position. All right. Remember shielding, deshielding? Let's make a statement about that. Working statement. In general, lower electron density is going to equal higher chemical shift, or delta value, or ppm position. Okay, ppm value. And a higher ppm value is going to be more downfield. All right? Ultimately, lower electron density, more downfield. All right? That's probably the way you want to think about that at first. But there's a little bit more to it than just electron density. We also have hybridization effects. Ultimately, let's just sort of go through the tables of peak position. This is sort of a general table, proton peak positions, and this is a little bit more specific. Here we go. In general, H's that are on sp3 carbons are going to be in the range of about 1 to 4.5 ppm. All right. H on sp3 carbon, H on sp3 carbon, H on sp3 carbon. The one exception to that is the H on the sp carbon also appears in this range at about 2 ppm. Okay, about 2 ppm. Typically, I would call these saturated CHs. Okay, saturated CHs are going to occur about 1 to 4.5 ppm. Now, it can be less than 1, you know, maybe 0.5 or 0.8. All right, somewhere in this range. All right, but let's sort of distinguish between these types. All right. Standard alkane, just like butane or hexane, these are going to be like 1 ppm, 1.5 ppm. If we start having an electron withdrawing group or atom, okay, like a nitrogen, oxygen, or halogen, all right, maybe something like this, which we've seen before. These bond to the X group, or Z. In this case, they're using the Z, okay, Z group. The carbon is bonded to a Z group. These H's here are going to be about 4 ppm. All right? Or I'll do this, about 3 to 4 ppm. How about that? Let's broaden it out a little bit to match the table. Something like that. Or maybe an alcohol. All right? That is, this is downfilled compared to just something like this, where all these are going to be like about 1 ppm. All the H's here. Now this is going to sort of tell off the effect of the electron withdrawing group, moving the electrons away from this site. And that's a de-shielding effect. It's like it's removing sunscreen. These H's thus feel more of the magnet, and thus the delta E is going to be larger. It's going to take more energy for the absorption to take place, and that moves the signal downfield. But the electron withdrawing nature kind of tails off, and this is going to be about 2 ppm. And then once you get sort of further away, it's going to go back to sort of standard position of about 1 ppm. All right, so that's sort of here. This is showing, I'm going to write a good bit here. You may write sort of different place. So your handout doesn't come quite as jumbled as mine may be. This is showing still an sp3ch, but like a carbonyl. Now there's no hydrogen on this carbon. All right. Again, this is sp3ch land. But these H's over here, next to this electron withdrawing group, these are going to be about 2, I'll broaden it out a little bit, 2 to 3 ppm. Most common carbonyl, or this could be a nitrogen group, okay? Basically, standard alkane CH is about 1 ppm, but if you have an electron withdrawing group nearby, like a halogen or an OH or maybe an NH2 or something, or a carbonyl group nearby, it's going to move the signal downfield to more like about 3 to 4 ppm. Carbonyl is more like about 2 ppm. All right. The next region is sort of the sp2 CH. This would be your alkene hydrogens or vinyl hydrogens, H's that are on alkene carbons. They occur at about, I would tell you, about 5 to 6 ppm. That's what you're going to hear from me. Now this table says 4.5 to 6.5. That's fine too. All right, that's your alkene. They're more downfield. Not so much because of electron withdrawing group, but because the carbon being sp2, it has more S character. And so the electrons of the carbon are held tighter to the carbon. And so those electrons are not able to be as close to the hydrogen. So that's sort of my argument there. It's a hybridization effect. Okay, the next region is the aromatics. We'll call these aryl hydrogens. All right. I will tell you these are about 7 to 8 ppm. Classical aromatic region. Now it can be higher or lower than that. Okay. So can these. These not so much. Aromatic region, 7 to 8 ppm. Have we seen such before? You remember the spectrum overview? Remember the aromatic hydrogens? We said they were here. See? About 7 to 8 ppm. We got a signal in this 3 to 4 range. That'd be the CH2 because it's bonded to the nitrogen. That would be an example of such where the Z group is a nitrogen. Then we have the NH2 group. That's going to be a little bit more variable, and we haven't mentioned that yet. Okay, a couple of outliers. Aldehyde CH. All right. It is an sp2CH like this. But because it's also got the electron withdrawing group, aldehyde CH is about 9 to 10 ppm. Aldehyde. Typically 9 to 10, your aromatics are not going to be that far downfield. So it's a unique region which is usually, if you see a peak there, it's going to indicate an aldehyde. Of course, not always. Okay, one other one we could say, carboxylic acid. This is going to be downfield, okay? 10 to 12 ppm. This is the first hydrogen we've seen that's not on a carbon. It's on an oxygen. And one word of caution. When H's are on oxygens or nitrogens, the peak position can actually vary somewhat. All right? And tables are a little bit less reliable. All right? Or they're going to give you a broader range. Carboxylic acids, though, I've seen, you know, something 14, 15 ppm, way downfield. Kind of odd. All right, that's the general range. Most protons are going to be those types. Oh, let's go back here. We went from sp3ch, sp2ch, but what about the spch? It's actually back upfield at about 2 ppm. So it's not really a trend there. The reason why is worth explaining. It's an anisotropic effect. It's sort of shown down here. Aromatics about 7 to 8, alkenes about 5 to 6. This is sort of the other way. About 2.5 ppm. Now the sp3 carbon is actually more electron withdrawing because it's 50% S character. All right. We need to look at the anisotropic effect. It also helps explain why the aromatic CH is more downfield than the alkene CH, while they're both sp2CHs. Aromatic more downfield. The anisotropic effect is explained over here. Anisotropic is basically a fancy term for direction of the field. We can look at that first with aromatics. Okay, the aromatics has a nice ring current. That current is really induced by the external field. Well, I don't think that's quite right. It induces a second magnetic field. But that magnetic field circulates in this direction here, and the arrows are shown. But out here where the H sits, this induced magnetic field is coming this way, and it's actually lining up with the B naught. All right? And so it reinforces the external field. And that is actually not a shielding effect. It's actually a de-shielding effect. Okay? Because it's not acting like sunscreen. It's not diminishing the sun or the magnet. It's actually adding to it out here. That's like putting, not putting on sunscreen, but putting on something that's going to cause you to become sunburned even quicker. And so that's the opposite of shielding. Sunscreen shields, but if you put something on that does the opposite, we would call that de-shielding. And de-shielding we know is going to move the signal towards the left, more downfield. And that's the reason why your aromatic hydrogens are more downfield than your alkene hydrogens. The reason being that the magnetic field from your aromatic is stronger than from an alkene, and I think I mentioned that up here. So the electrons in the aromatic are going to lead to even more de-shielding than what the alkene would do. Now, on the other hand, let's look at the alkyne. The alkyne, the electrons circulate in this manner. Okay? All right? It turns out that the H, because the alkyne is linear, if we can make this bigger, okay, like this. All right, that's turning and circling, make that bigger. Where the H sits, the field is actually opposing the external. and opposing is the shielding effect. All right, because it's going to subtract. Up here it's actually adding to the external. Subtraction is the shielding, and shielding is going to move the signal to the right, and that's actually why the alkyne, instead of going sp3, sp2, and then maybe sp, actually the sp goes the other way and sits more upfield at about 2 to 2.5 ppm. This is all called anisotropic effects, meaning direction. It all depends on the direction of the field, okay, and where the proton sits. All right. Okay. Here's a sort of another table. Sort of goes over the same thing we did, but more in sort of table format. Type of proton, chemical shift. Plain old sp3ch is about 1 to 2 ppm. Okay. You don't have to get so much in detail. Ultimately, once you start working problems, you'll sort of learn of what level of detail do you need to know. We mentioned these. There's your SPCH. Okay, electron withdrawing group on the carbon where the H sits. Everything's here, right? Aldehyde 9 to 10, yeah. The one thing that show here is that your OHs and NHs, now this being alcohols and amines, these tend to be about 1 to 5 ppm. Okay, all right, but highly variable. Also, OH and NH signals are often also broad rather than sharp. Okay, and so the signal may sometimes be like this as opposed to sharp like that. All right, broad. We'll talk more about these types. We'll also introduce the DTO Shake, which is going to be our fifth sort of concept. The DTO Shake will help us determine if a signal is from an OH or NH. To go back over here, remember spectrum overview, aromatic hydrogen 7 to 8. Then we have these two. The NH2 is here. CH2 is here. Because the carbon's bonded to a nitrogen. And so we would expect this to be downfield, about 3 to 4. Indeed it is. And then the last signal we can assign to the NH2, about 1 to 2 ppm. And that does fall in the range as indicated here. All right. By the way, Bruce was a book that we used a while back. I'm sure that the Klein textbook will also discuss anisotropic effects. Okay, before we move on here, I can make a comment about carbon NMR peak positions. Whenever you're looking at carbon NMR, we're going to use the 20 times rule. All right? For example, the H is on this carbon about 3 to 4 ppm. Well, the carbon itself, okay, CNMR, it's just 20 times this. So it's going to be about 60 to 80 ppm for the corresponding carbon. All right? And that's the so-called 20 times rule. Now, when we get over to the carbon NMR section, we'll also see tables, and we'll look at that closer. So this is a little just prelude to that. It's actually more like about the 18x rule, okay? But usually it's just sort of stated generically as 20x. Not that precise, but it does get you in the ballpark. All right? For example, as another example, aromatics. All right? Again, don't write so much on your handout probably. You want to be selective, or maybe write on a different page as we go through this. Whatever you think's best. 7 to 8 ppm for that. And so the corresponding carbon, we would expect 20 times that, so that would be 140 to 160 ppm for the corresponding carbon that the H is on. Again, it gets you in the ballpark. Actually, for benzene, it's about 130 actually. So it's not quite 20, it's more like 18 or 19, but 20 is a little bit easier to remember. Okay. Here's another table. At this point, this table was pretty much just for your reference. I think we've covered most of the general positions. Okay. Some of this is repeat, like the variability of these guys. You sort of have to just learn to what extent do you need to know your peak positions. But you also dealt with this with IR. Okay. Ultimately, you need to be able to work problems and to use NMR as opposed to memorizing every peak position. Okay. So some of this can be just for reference for you to look at as needed. Okay. Next topic or concept. Signal integration. We've alluded to this before, but it turns out for proton NMR, the signal intensity correlates with the number of protons that signal is for. That is, the area under the peak is related to the number of hydrogens for a given signal. That's just another way to state it. Now, this does not always apply for carbon NMR, but it does apply very well for proton NMR. Integration is very commonly used for proton NMR. Integration is not as useful for carbon NMR. And this is due to the slow relaxation of carbon. But we will mention this later once we get to carbon NMR. Let's look at the integration for a proton NMR. Let's look at this compound here. Number of signals. I expect one signal for the methyls and one signal for the CH2. Right? Two signals. A and B. I would expect B to be more downfield. In that sort of 3 to 4 range, because it's the carbon is bonded to an electron withdrawing group. All right. And that's what we've done this far, right? Let's make sure we have two signals. Indeed we do. Two signals. One of them is more in the 3 to 4 range. Indeed it is. The other is sort of removed from the electron withdrawing group. It's going to be more upfield. Now it's actually twice removed, because the H's are not on the next carbon, but they're on the next one. So pretty much it's gotten us back down to that one range where sort of standard alkane CHs give peaks. Okay, so number of signals and peak position is here. TMS, right? Remember TMS? A little bit of TMS. It's not quite on 0 there. A wee bit off, but essentially it's on 0. But let's look at the integration. How many AHs are there? There's 9. 9. How many BHs? There's 2. We should expect that the intensity of these signals are, the intensity is in a 9:2 ratio. All right. Now this is A and this is B. This signal should be, or we can take this down to what, 4.5 to 1, right? This signal should be 4.5 times more intense than that signal, because the signal correlates with the number of hydrogens. Now, how will integration be given to you? The older and standard instruments used an integral line, which sort of scopes over the signal, comes up here, it's coming here, and when it gets to the signal it rises and then flattens back out. Here it rises, doop, and then flattens back out. And basically you sort of chop that line from where it starts rising, all right, to where it sort of flattens out. Boom and boom. And then you measure that, all right? You actually pull out your ruler and say that this was, I'm going to say 1 centimeter, where this here was it's less than 4.5, it's like 3.8 centimeters. All right, that's a little bit off. I'm seeing a 1 to 3.8 ratio. It should be 1 to 4.5. Now, integration is not always going to be exact. Now, whenever I present this handout, I've never measured this before. I've never been sitting at my desk. But that's where you take this ratio, and then we can turn this into number of hydrogens. And of course, this can become 2, and this can become 7.6. All right. Of course, you can't have a 0.6 hydrogen, so maybe this is 2, and this equals 8, 2 to 8. The integration looks sort of like 2 to 8 to me instead of 2 to 9. All right. But let's also look at this. Some instruments will give you a computer-generated integration, and that's what we're seeing here. 1.6. I don't know what that is. That's not a centimeter. That's just a computer-generated number there, almost unitless. Relative numbers. It's not 1.6 centimeters. But these numbers is basically your integration. And it's giving me a 1.6 to 7 ratio. All right. Well, you can't have 0.6 hydrogens. One way to do this is to divide both numbers by the lowest number. Divide this by 1.6, divide this by 1.6. This becomes 1, and 7 divided by 1.6 7 divided by 1.6 equals 4.4. Alright. It's actually 4.38. At this point, this is a ratio 1 to something. The problem is you can't have 0.4 hydrogens. And I'm guessing this is probably a half. Let's double this to 2, and if that was a half, that becomes 4.5 times 2 is 9. And we get the integration, which is ultimately what we have. We have 2 B hydrogens, and we have 9 A hydrogens. Okay. Now that was an intro to integration. As we go along, we will do more and we'll approach it differently and we'll try to fill in the blanks here. Now there's a problem here to work. A compound of molecular formula this gives the following NMR spectrum, which is integrated. How many protons give rise to each signal? All right. This is something that you can do on your own. You do this. Again, these numbers don't mean anything in themselves. This is just a ratio. And I sort of showed you how to work this. Also, you don't have to measure integral lines. They're giving you these numbers. If they didn't give you these numbers, you'd have to get out your ruler and measure the integral lines and then go from there and establish your own relative numbers. Okay. Actually, I said you do this, sort of the answer is below. Don't look at the answer. Okay, it sort of takes you through. This is from another textbook. There should be problems like this in the introduction part of the NMR chapter in your textbook. This is something for you to do on your own, sort of analogous to what I did above. But keep in mind, though, we don't have a compound here. All right, we're starting with the integrals. Up here, I sort of started with the compound, and I established the 9:2 ratio just from compound. All right? We need to be able to work just from spectrum, and that's what we're doing down here. Okay. We're making some progress here. Let's look at this compound, and we have a proton NMR. Number of signals, well, that's already given for you. Okay, 1, 2, 3, 4, 5 signals. Hopefully that makes sense. Because of symmetry, these two methyls are the same. Make sure you understand that and realize that. Now integration, since we have structure, integration just comes from number of protons. The A signal is 3. The B signal is 6 because there are 6 H's that are B. The C signal is 2. The D signal is 2. And the E signal is 1. Okay? So we know what integration we expect. Really, I'm going to kind of end this video right here, and I want you to think about the multiplicity or splitting. Okay, I'll call it splitting. What splitting do we expect? Signal A. Okay. Now, as we move ahead, we'll learn that signals can be, singlets, doublets, triplets, quartets, or multiplets. They can be split into, they can be not split, just one line, split into 2 lines, doublet, split into 3 lines, triplet, split into 4 lines, quartet. If it's more than 4 lines, we typically call it a multiplet. Okay? What type of splitting would you expect? But the other thing is peak assignment. Peak assignments. That is, which signal in the NMR is for A? Which signal is for C or D or E or B? Okay, assign these. You can assign these by basically writing the letter above each signal. Now you'll mainly at this point have to do that based on what peak position do you expect. Once we learn splitting, you can look at the signal and look at the structure, and you can make assignments based on splitting. All right. But here's what I'd like for you to do is first, you're going to have to assign signals first. Once you assign A, okay, assign it, then you can look at it and tell if it's a singlet, doublet, triplet, quartet, or multiplet. All right? I'll do the first one for you to show you what I mean, to make sure it's clear. Which signal do I expect to be more downfield? Which of these signals most downfield? By the way, this NMR is showing 5 signals, 1, 2, 3, 4, and 5. But they're also showing you an expanded view of 2 of the signals. See, this is 1 to 1.3 ppm. This is the expanded view of that signal. And this, 4.8 to 5, is the expanded view of this signal. They're expanding it so you can tell how many lines are there in this signal. And this is 1, 2, 3, 4, 5, 6, 7 lines. And that's going to be a multiplet. Because when it's above 4 lines, we start just calling it a multiplet. All right? Where this signal is 2 lines, okay? And that's a doublet. Which signal is this? Is this A, B, C, D, or E? All right. And whichever letter it is, we're going to, in the multiplicity, we're just going to write M for multiplet. Okay? So if it's for A, we would just write multiplet here. But it's not A. Okay. Try to fill in the multiplicity that we see. We're not predicting multiplicity. We're really predicting peak position, and then we're just looking at what the multiplicity is. All right? But practice on just looking at these peaks and telling if they're singlets, doublets, triplets, quartets, or whatnot. Try to do peak position and fill in the splitting that you see for each signal, and let's see how you do here. And then we'll move from there. Okay? That'll give us an introduction into splitting. But we'll first have to talk about, why does splitting occur? What causes the splitting of the signal into like a doublet or a triplet or a quartet, etc.? Okay guys, we'll end video 2 there, and we'll pick up with signal splitting in video 3.